discussed earlier, a huge interval is going to be pretty useless. Okay? Okay, yeah, it's really easy for me to say, hey, you know what? I am 99% confident that the proportion of vanilla ice creams that our students have is between, 2% to 98% of the ice creams they eat. Okay, so that's useless. That huge interval is useless. So we're going to discuss the things that change the size of the interval. We're going to examine, so we do that by examining the formula, which you used yesterday when you did your computation. The statistic, which is your p hat, times your critical value, which is based off your z-score, times that standard deviation of the statistic. Now, we want to really hone in on this piece of the formula. This piece of the formula is what is called the margin of error. And so let me give you a graphical picture of a confidence interval. If you were on a number line doing an interval, you would put a dot for your p hat, your statistic, and then go out for the upper bound and down for the lower bound, and those are symmetrical because you go up this margin of error and down the same margin of error. Okay? All right. So, let's address each one of these following items: statistic, critical value, standard deviation, and see how are they changing the size of this interval. And so here we go. Statistic, that's the sample you take. That's the value of the sample you get. How do you think that's going to change the size of the statistic? The size of the confidence interval. How do you think that statistic is going to change the size of the confidence interval? Let's see. Is it going to change the spread? No. Okay. It's the sample that you get. It does not change the size of the interval. It changes just where it's located. Does that make sense now? Let me show you a better picture. Here we go. Here, let me kind of guide you through what this is. Here's a graphical representation. This brown line here at the bottom is something that, in theory, is what is the real truth, but you don't, it's hidden whenever you really are in real life. You don't actually know what the true p value or the mean is, true p or proportion or whatever. This black item is the confidence interval, and the dot in the middle is the sample you get. And what is this whisker up here to the side? That's going to be the margin of error up, and then this whisker down here is going to be the margin of error down. Now, if this interval is colored black on this screen, then it contains the true answer, the true proportion of whatever. But if it changes to a red, then it's not. See, like that? Then this one is one that does not contain the true proportion of whatever. So I have set this so that I have 10 items in my sample size. You know what? Oh my gosh, that's not large enough. Maybe that's not large enough. How can I still have hope in using this? If the sample is not large enough, it's okay. If the parent population is normal, then anything that drops down is okay. It's going to be normally distributed even if it's too small of a sample. Hey, get that, people? On the test, that did not happen. We had some people that said, oh, the sample size is too small, 20 is less than 30, so the normal model does not apply. But I will continue with caution, and thank goodness you did, because then that actually did the rest of the problem and it saved you. But if you stopped right there and just one or two people did, then you lost all the rest of the stuff, because actually the normal model applied because the parent population was normal. Okay, so back to this. Sorry, that was a little sidebar. So this is going to demonstrate a sample size 10, confidence. See this C? This is a confidence of an 80% confidence. So now, this random C, that just means the random they have, this is the 295th sample that they got. I'm just going to go up so we can see these samples. So watch these samples, getting different samples. What's happening? They're jumping all over based on what the sample proportion was. How about the width of the confidence interval? It's not changing. It's just moving up or down based on its value. Now, again, why are some of these coloring up to be red and some of them black? Correct. The black ones will contain the true population parameter. The red ones were a sample that missed out. Okay, I'll show you.
There it is.
This is a sample right here. This p-hat made an interval that ended up not capturing the true proportion of whatever. Okay? Quiz or test? Okay. All right. So, one thing real quick and then we'll go on. Guess what? Here's what this means. You see that this is a confidence level of 80%? 80% of all 80% confidence intervals are going to capture the real answer. So if I move up and down this, and I counted how many of them were red and how many of them were black, 80% of them will contain that true proportion, that true answer, and 20% wouldn't. Okay? This one, these are good. Okay, but that's a sample that you got that does not contain the true answer. Okay. All right, so that's the statistics. So we got this going on. Statistics. So right down there that the p-hat does not actually change the size of the sample, it changes the location of it. Okay? So here we go. P-hat does not change the size of the interval, just its location. Okay. All right, now let's talk critical value. Up here in our formula, here's the critical value. Okay. What did we learn yesterday that the critical value is derived from? Good. The z-score, and that z-score happens because of the normal model and how, what? How confident you want to be. So watch this. I'm going to have a few normal models here. I'm going to clone these. You are getting better. Okay. Got some good curves? Okay. So here we go. Watch this. 80% confidence interval would have, of course, our critical values located where 80% is in the middle. 90% confidence interval is going to have critical values so that 90% is in the middle. And if we go, say, to 99% confidence interval, we're going to have critical values such that 99% is in the middle. What is happening to the width of the interval as it increases in confidence? Good. The interval is getting larger. Why? Because I have to be more confident that I captured the true value. See? I have more confidence. Yep. More confidence equals a larger interval. Okay? So let me demonstrate some of that. Here we go. Okay, so here is this. We'll just pick a random one there. Okay, watch the confidence level as it goes from 80% up to, say, maybe your boss says, excuse me, 80%, this step is life or death. I don't need to be 80% confident that there are no mistakes. I need to be, 99% confident because I don't think you can really be 100%. So here we go. Your boss wants you to be more confident. Boom. What has just happened? So then you're saying, yeah, I'm 99% confident that the amount of errors in the sample are going to be from 30% to 100%. Okay, you think that's going to fly?
No.
Yeah, your boss is going to say, excuse excuse me, no. You may be more confident, but this interval is way too big. I'm just making numbers up. This is way too big. I want it smaller. So let's see how we can get it to be smaller. Here we go. Yep. All right. To make this thing smaller, we can affect this standard deviation of the statistic. Because if I make this number smaller, then it's going to make this whole product, this whole margin of error smaller, which will make that whisker smaller and the intervals smaller. So I have a way of making the standard deviation smaller. So if the standard deviation gets smaller, then we have less variation. We are clustered more closely around our sample. So we have less variation, which is meaning a smaller interval size. Smaller size interval. Okay. And so with a formula such as this, what is it that we rely on to make the standard deviation smaller?
The number of samples.
Okay, increase in. And you will need what you need. Increase the value of the number of samples. Okay, so here we go. Let's watch this. Yes, your boss wants you to be 99% confident, but this size of this interval is ridiculous. So, take more samples. Watch this interval. Okay. Do you see? I'm 99% confident that I'm capturing the true value, and this is a reasonable size interval, hopefully, for the whatever it is. Okay? All right. So it's a balancing act. If you increase the confidence, how can you counteract this interval getting bigger? Increase the sample size. Okay, that would just have to be with which random sample happened to be done. It's just a bunch of different random samples that happen, like all the different p-hats. Okay. All right, one last thing. Let's say we want to be 95% confident, but you work for a fireworks company, and you need to come up with a proportion of defective fireworks in the sample, so you can infer that to the whole population of your fireworks that are that type, and see if the machine is, or your assembly line of people or whatever is not being very accurate. Okay. So when you get to doing that, how do you test those fireworks to see if they're working? Yeah. You blow them up. Then they are no longer good. So you are destroying the product in the process. So do you think you as a manufacturer are going to then limit the sample size? Absolutely, because it's something that is then irreplaceable. So, it may be set to say 30 or whatever. Then if you need, if you don't want this to be this large, maybe then you're going to have to back your confidence off to make the interval smaller. Okay? All right. So that's what's going on. That's the give and take of the confidence level and the sample size. All right. So here we go. We have already identified the margin of error, and we identified how it changes the size of things. So let's go to this example. Presidential Pete. Presidential Pete is on the home stretch of his campaign, and he wants to know if the polls predict that he will win the election. Well, a recent poll of 1,020, which the Gallup polls around 1,000 when they do theirs, randomly selected voters and found 484 responded in favor of Pete. Construct a 95% confidence interval for the true proportion of voters that are going to vote in favor of him. So he wants to know where does he stand. We're going to actually construct it in a second on the back, but let's answer these changes in size questions. Here we go. How would raising the confidence level to 98% change the interval. He wants to be more confident. That's right. If you want to be more confident, from 95% to 98%, here, let's watch it. Actually, it'll be a little more dramatic maybe if I have a smaller sample size. Here we go, 95% to 98%. Okay, that's going to increase the accuracy, I guess, of your interval. Okay, so next question. Oh, wait, let's write our answer down. So it makes the interval bigger. All right, Pete wants another poll, but you know what? We're at the end of the road, and we're running low on campaign funds. So the campaign money is getting limited. So we have to only be able to poll 500 voters. So all else being the same, how's this going to change? How's this change the sample size? What's it going to do to the interval? Okay, smaller, N is smaller. So now I'm having less accuracy. I'm having less accuracy. So smaller sample size, the standard deviation is increasing, so that whole margin of error is increasing. This is kind of the train of thoughts. So the interval then is what? It's going to be larger. Yep. Okay, let's watch it over here. Okay, let's say these are times 10. So here we got our 1,000 people. Let's change it to 500. So let's watch what happens to our accuracy here. Okay, so what happened to our interval? It got larger. Okay, less sample, larger interval. Okay, so that is the gist of what's happening. Now, when we go over here to the back, we're going to look at an acronym. It's called the PANIC model, and that's how you make a confidence interval, and it's a template to help you know and to make sure that you include all the little details and all the little things that you're supposed to include, okay? So let's go through this problem, and it is called the presidential pitch problem. So here we go. Yes. So the first thing we have to do is the population parameter. The population parameter is what we are hoping to estimate in the end. And so what is our end thing that we are hoping to make a claim about in this problem? Okay, maybe you need to go to the front and read the little paragraph to think about what are we hoping to estimate or be able to say. Thank you. Right here. Hey, this isn't frequently written for you word for word in the problem. So you need to always search for it. Okay? You don't need to make it up. It is frequently written for you. Just find it. So our p-value that we are going to be doing is the true proportion of all voters, because I need to emphasize that we are coming up with something for the whole population. So it's the true proportion of, and I always like to put all in there just because you are knowing that this is about the population. This is what you are inferring to. True proportion of all voters that will vote for presidential P. Okay, so in the end, that's what we're going to be making a claim about. Okay, our assumptions and conditions. These are our favorite things. So let's get real, people. Okay? So here we go. What's first? Do not put RIL. We're going to have to, I don't know what. I would like to say hurt you, but I would like my job. And okay? No, it's not. It's a leftover. Sorry, little inkling. Okay. You did get one. Okay, random. That's a lecture for me. Sorry, it was pretty wimpy.
And then she ended up doing it.
And then I ended up doing it, so. I know, see, I'm just like that, sorry. I know, see, y'all are used to all the coach lectures, but I'm nothing like that. Yeah. Okay, here we go. Random. Your choices are stated or assumed. Hey. Stated or assumed a representative sample. So what do we got here? Yep, this one is stated that the sample was randomly selected. Okay, so here we go. Stated. All right. What's next? Independent. Okay, so what does this little thing here tell about what's going on? Hey, I understand that it's less than 10% of all. I mean, but why do we check the less than 10% of all things?
To see if it affects the bigger picture.
Yep, we do not want one sample affecting the probability of what's happening in another sample. From sample to sample, the probabilities are not changing. That's what we're going for. So we say that our sample of 1020 is less than 10%. And if you stop right there, that's a mathematical lie. This says 1020 is less than 0.10 or 0.1. Yeah, no. So it's less than 10% of all voters. Okay, now that's true. Do you think that's reasonable that 1020 is less than 10% of all voters in the presidential election? Okay. So our last one is large enough. And since for the next 4 chapters we are doing proportions, then our way to do this is NP and NQ are greater than or equal to 10. Now, let me kind of show you something here, because you might miss this, and then you're going to be like, oh, duh, I actually missed it during first period, and then second period I was like, oh, yeah, okay. So, watch this. N, and if I write the P hat as a fraction for a second, you're going to watch this. 484 out of 1,020 is the ones that voted for presidential Pete. So, in essence, how many successes do we have? We have the 484. So kind of you didn't actually need to write the NP because it was told to us that the number in favor, so the successes, is 484. Okay? So don't lose sight of some common sense in that regard, because I have a tendency to do that. So 484 is greater than or equal to 10. Ta-da! Which makes the other portion, the failures, the ones not voting for presidential Pete, is 536. And that is greater than or equal to 10. So one question before we summarize our conditions. Question is, what are we going to do if this is not large enough? It's not large enough. Aha! Good. If it is not large enough, there is still hope. You can go up there and check the paragraph again and see if the parent population is normally distributed, because if it is, boom, then anything that drops out of it is normally distributed, even if it isn't large enough, so you're covered. All right? Kind of in essence, if the parent population is said in the beginning to be normally distributed, then you're large enough. It's kind of like an automatic done deal. It's going to happen. Okay? You could probably say at that point, stated parent population is normal. I don't know. I'd probably, yeah, you can do that. No, you can say the parent population stated normal. Yeah, that'd be fine. Okay. Last, final conclusion to our conditions. Thank you. Yes, normal model applies. Okay, if you have not put that, then you've just like lost the whole point of conditions. Are you wanting to do the test? Yeah, put your number. Okay, next, this is new. You have not learned the name of what we have been doing. What we have been doing, and there will be like 12 other things that you're going to learn the names of that you have to identify. But this first one that we learn is a 1 proportion. Z, because it's built off the normal curve and the critical values are z-scores, interval. 1 proportion Z interval. Ta-da! So you write that down, and now we're going to do the computation. Here it is. So, and by the way, none of the stuff that I'm writing down is excessive in any form. It's all required. The first thing I'm going to do is kind of write all my little information over here from the front. The sample size is 1020. What else do you think I need to write down? How about our sample p-hat that they gave us? Okay. That was 484 over 1020, which I'm going to tell you is 0.475. All right. What else? Okay, yeah, we can go ahead and do that, and then we'll do that. Standard deviation of the sampling distribution is the square root of 0.475, 0.525 over 1020, and I'm going to go ahead and tell you right now that that's 0.0156. Okay, one last thing that you want to identify. Okay, it has to do with the confidence level, so what is that we're going to identify? It's called the critical value. And yes, you go off to the side and you compute that it's inverse norm of 1 tail at 95% confidence, which is what is stated they want. 95% confidence, what's in 1 tail? 0.025, so that critical value is going to be 1.96. All right, now let's do this thing over here. Statistic plus or minus the critical value times standard deviation of the statistic, and then you can plop out the answer. It needs to be in decimal form here, 0.444 up to 0.506, and you know that you are putting these from least to greatest, always, okay? And the percentages comes in when we write our conclusion in context, because this then should be something that you're able to say to somebody that would make sense to them. So in conclusion, how you want to start this?
In conclusion.
I am, yep, I'm 95% confident.
Sure. Can you put sure?
I just use confident. Okay, that the true proportion. Okay, make sure you know you are inferring to the population. You're not saying something about your sample. You are saying about the population. That the true proportion of all voters that will vote for presidential heat is between, here now use common sense ones, 44.4% and 50.6%. Now, that's it. But before we finish this, I have to enlighten you as to something that is very counterintuitive. Because I bet you naturally want to look at this interval and say, he's probably going to lose.
You can use normal model.
But we technically cannot, okay, here's the deal. Yes. You cannot say, even though we want to say that, look, more of the interval is on the losing side, right? Okay.
There's still a chance.
You could have easily gotten a sample because of sampling variability. That is the flip-flop of this. You could have easily have gotten an interval that was the flip-flop and was maybe from 49.4 up to whatever 55.6 or whatever. You could have easily gotten that. The point is this. You do not have the right to say it is more likely he will lose the election. Because according to this, there is a chance he will win. So all you can say is, basically it's inconclusive. He might win, he might lose. Don't say it's more likely he will lose. Bad. What if we had an interval that was completely contained below 50%? Then yes, you say, I'm 95% confident that he is going to lose this election because it's going to be from da-da-da-da-da-da, and that's all below 50%. But if it is not completely contained below the mark, this is a possibility just as much as anything below here is. So that's the one little kind of counterintuitive thing. All right. I want to go to your homework, and I need to add something here. There's an issue. Because on this one, I forgot to tell you how confident I want you to be. So number one, I want you to create a 90% confidence interval. And I want us to kind of walk through number two together right now. The reason I want to walk through number two is this is the type of problem that students really struggle with. You have been told and you know everything how to do this problem. But if you looked at this and if this showed up on a test, you'd say, you never taught us this. You'd go griping about my test saying, we didn't learn any of that stuff. But yes, you have. It's just thinking of things in a new and different way. And I'm sorry, people, but that's real life. That is real life. When you go to do your job, you're not going to see the real problems just exactly the way you saw them in high school. You're going to have to take what you learned in high school and apply it in a new and different way. So here we go. It's backwards. Thinking on this one. What fraction of cars are made in Japan? A Z interval for the proportion of Japanese automobiles with a 90% confidence. So that right there, you already are going to know your critical value. Look. The interval is given to you. And the confidence level is given to you. And you know what? From those two things, you now can figure out everything else you need to know about this problem by working backwards. So let's first kind of think of a picture of what's happening. An interval is essentially saying this. The lower bound is from 0.32 up to 0.48. So the first question, what is the sample proportion that is obtained? So in essence, what is the value of the p hat? Where's the p hat in the interval? In the middle. See? You know that. So how are you going to figure out what this value is in the middle? Yeah, I'm pretty sure, yeah, there's lots of ways you can figure that out. Add, subtract, average, whatever. What is it? Okay, 0.4. Okay, thank you. Now, what is the margin of error? How are you going to figure it out?
The Z interval proportionally scale.
I'm pretty sure we don't even have to do formula stuff here, but go ahead. Okay, how about look at the picture. Where on the picture is the margin of error? Pretty sure it's this little piece right here. That's the upper margin of error, and then there's a lower margin of error. How much is it from 0.4 to 0.48? Okay, thank you. So the margin of error, and you can abbreviate that as ME, is 0.08. All right. Now here's the part that really gets people. You can figure out the sample size from this. The reason you can figure out the sample size is because you know the margin of error. Got that. You know the p hat. We got that. You know the critical value, which, by the way, for a 90% confidence, what's that going to be? 1.645. You have all these things. So if you look at the formula, let me just write this here, you don't have to. Statistic, plus or minus the critical value times standard deviation of the statistic. Where is the margin of error on this picture? Thank you. Here is the margin of error. Okay. So let's set up an equation. The margin of error equals the critical value times the standard deviation of the statistic, which is p hat, 1 minus p hat over n. You know every single thing in that equation except for n, and then you solve for it. Ta-da. That is going through that process is understanding this forwards and backwards and being able to fully work through this problem. You learn it forwards, being able to do it backwards as well is what you need to be able to do. All right, so that's the only thing that I wanted to talk to you about, because I'm just tired of hearing, we never learned this. This isn't anything we ever did. It's not. I am doing you a disservice if I give you the same kind of thing over and over and over and over and over again, because you will not become a thinker, and in life you're not going to see the same thing over and over and over and over and over again. Okay, but anyway, so I'm going to come around and stamp you right now, and you've got a solid more than 10 minutes